In this last example, we're not going to sketch the full graph of the function. We're not going to go through all of those steps. The only thing I want to focus on are the asymptotes. So let's go ahead and look at this rational function here, x squared plus x minus 1 over x minus 1, and let's see what the asymptotes are. So let's start with the vertical asymptotes. What are the vertical asymptotes? Well, for this rational function, it seems that the only place a vertical asymptote could appear is when the denominator is vanishing, when x is 1. So let's go ahead and look at that. What happens when x goes to 1? We've got to go from either side. So what happens as we go towards 1 from the left? So that's x squared plus x minus 1 and x minus 1. As we head towards 1 from the left, the top goes to 1 plus 1 minus 1. So the top is going to 1. The bottom, as you head towards 1 from the left, slightly smaller than 1, this is going to 0 through negative values. So this is going to negative infinity. What about as you head towards 1 from the right? Notice at this point, we already know there's an asymptote there now, because it heads off to negative infinity as you go towards it from the left. But we can also see that something happens as well as you head towards it, as you head towards 1 from the right. So as you head towards 1 again from the right, in this case, you're still going to 1 on the top, but the bottom is x minus 1, so a number slightly bigger than 1. Take 1 away, that's a number slightly bigger than 0, so it's heading towards 0 through positive values. And you're heading off towards infinity. So x equals 1 is a vertical asymptote. Okay, so that's not the interesting one for this example. The reason I'm doing this example is because I want to illustrate a slant asymptote, but I thought it's worth just going through the vertical asymptote again. So now let's look to see whether there's a horizontal asymptote. So we head off to positive or negative infinity. So I'm going to head off towards positive infinity. Here it's a rational function. The numerator has degree bigger than the denominator, degree 2 over degree 1. So as you head off towards infinity, the numerator is going to blow up much faster than the denominator, and it heads towards infinity. And so we see that for rational functions, the same thing's going to happen as we head towards negative infinity. As you head towards negative infinity, it's going to also head towards negative infinity. And so we see that the function's blowing up. So there's no horizontal asymptote. But how is it blowing up? Is the function heading off towards infinity like a line does? Or like an exponential or a logarithm or some other function? Well, the point here is that it's going to grow like a line grows. That means we actually have a slant asymptote. And we'll see how we can detect this now. For rational functions, we can always do long division. Divide the denominator into the numerator and see what happens. So let's go ahead and do that. I'm going to divide the denominator into the numerator just to get another expression for this function. So if I divide x minus 1 into the numerator, it goes in x times, gives me an x squared minus x. Take their difference, x squared minus x squared is 0. X minus x, that's 2x. And then we got a negative 1 there. And x minus 1 goes into 2x minus 1 2 times. So there's a plus 2. So that's a 2x minus 2. Take their difference, and that's a value of 1. So what does this long division tell us? Well, it tells us that this thing multiplied to this thing added to the remainder is equal to what's sitting under this division bar. So let's write that out. It says that what's under the division bar, x squared plus x minus 1, is equal to x plus 2 times x minus 1 plus our remainder. Why is that useful? Well, notice that this is the numerator of our expression. So what we have is that x squared plus x minus 1 divided by x minus 1. That's now our function that we're interested in. I've rewritten the numerator to see how many times the denominator goes into it and what's left over. So now I can divide x minus 1 into both terms of my newly rewritten numerator, and I get an x plus 2 plus 1 over x minus 1. And this is the key thing to notice. As x gets really big, what's happening here? Well, this 1 over x minus 1 gets really small. It becomes negligible. For really big x, this doesn't contribute pretty much anything to the value of the function. The value of the function is mostly, therefore, determined by x plus 2. So our function looks roughly like the linear function x plus 2 when x is really big. So for x big, f of x approximately looks like x plus 2. So y equals x plus 2 is a slant asymptote of f of x. Okay, so we've got a slant asymptote. The function's blowing up, but it's blowing up roughly like x plus 2 is. Let's go ahead and look back at what the definition of a slant asymptote was, just to see that we've captured it. Slant asymptote is a line, y equals mx plus b, if the difference between the function and the line heads to 0 as x goes to infinity. Let's make sure we've got that. So let's check. Let's check that this is the case from our definition. So I'm going to look at the function, f of x. I'm going to take away x plus 2 from it, and I'm going to look at the limit as x goes to infinity. If I look at my newly rewritten form of my function, I see that if I take x plus 2 away from my function, all I'm left with is this 1 over x minus 1, which clearly goes to 0 as x goes to infinity. So x plus 2, y equals x plus 2, is our slant asymptote. So that's one way to get at our slant asymptote, is to, in the case of these rational functions, do long division and work out the details and see what happens, as we've done here. There is another way to get at a slant asymptote, one that works more generally for functions, and that is, well, let's just illustrate it here. So how to find m and b. So how do we find m and b? Well, the idea is, let's compute the limit as x goes to infinity of our function divided by x. And that, when we work out the limit, will give us our value m. If this limit exists, it'll be the value m that we're looking for. And once we have that, we can take the limit as x goes to infinity of f of x minus that newly computed m value times x, and that will give us our value b. So that's how we can compute them. Why does this work? Well, the idea is if this limit, if the difference between f and mx plus b is 0, then just dividing through by x is also going to have a limiting value of 0. And just so maybe we'll do a quick little proof here. So if the limit as x goes to infinity of f of x minus mx plus b is equal to 0, then, let's move it all the way up here, then what? Notice my assumption is I'm assuming there's a slant asymptote, so I'm assuming that this limit is 0. Then the limit as x goes to infinity of, and I'm going to divide everything by x. F of x minus x, and I'm going to divide it into each term, so minus mx over x, that's just m, plus b over x. That limit also has to be 0, because if the original function here, f of x minus mx plus b, goes to 0 as x goes to infinity, then sticking an x underneath it makes it go to 0 all the more faster. So this has to also be 0. But also notice that that thing is going to 0. b over x goes to 0. So the difference goes to 0, but b over x is already going to 0. So that means f of x over x minus m has to go to 0. So that means that the limit as x goes to infinity of f of x over x minus m has to go to 0. But therefore that means that the limit as x goes to infinity of f of x over x has to go to m. So under the assumption that the slant asymptote exists, the limit of f of x over x as x goes to infinity must equal the slope of that slant asymptote. And so that's how we can compute it. Okay, so let's go ahead and check to see if this works. So let's do this as an alternate method. Alternate. So we're going to go ahead and we're going to work out the limit as x goes to infinity of f of x over x. If the slant asymptote exists, this is going to be that slope, m. So this is equal to the limit as x goes to infinity of what was f of x over x? Well, this was x squared plus x minus 1 all over x times x minus 1. Quadratic over quadratic. The n behaviors determined by the ratio of the leading coefficients. That's 1 in the top, 1 in the bottom, so its value is 1. So there's our m. How do we find our value b? Well, I take the limit as x goes to infinity of f of x minus m times x. m is 1, so just minus x. That's the limit as x goes to infinity of x squared plus x minus 1 all over x minus 1 minus x. So now we go ahead and put those over a common denominator. The limit as x goes to infinity of x squared plus x minus 1 minus x minus 1 times that x over there. So that's a minus x plus, minus x squared, sorry, plus x all over x minus 1. And we see that we've got some cancellations happening here. The x squared cancels. We get an x plus an x in the top. That's a 2x minus 1. The bottom is an x minus 1. So the ratio of the leading coefficients would be 2 over 1, or 2. And that's our value of b. So this tells us then that the slant asymptote is y equals m, which is 1, times x, plus b, which is 2. So either way, we got the same result. So what does a slant asymptote actually look like in terms of the graph? So let's plot our function. So we've already seen that there is a vertical asymptote there at 1, and we know its behavior around it. The point here is, how is this thing blowing up? What's the end behavior? So we're going to just rescale our axes to bring it into perspective here. And we can see that it looks like it's heading off towards infinity, sort of like a linear function does. What kind of linear function is it behaving like? Well, that's what we worked out. We saw if we go x plus 2 and sketch its graph. I'm going to change the color of that so you can actually see that it plotted it. So let's change it to red. Then we can see that the function is heading off towards infinity, much like a linear function does. That's what it means to be a slant asymptote. The function's blowing up, but it's blowing up like this linear function y equals x does. It's heading off to infinity in the same way. So that's a slant asymptote. All right, that's it for this section. Thanks very much for watching, and we will see you again next time.